Thank you all for watching our presentation. We are talking about making caramel. Caramel is a very temperature-sensitive candy. The structure of the sugar crystals changes based off of temperature, and so the difference between caramel hard candies and chewy caramel is the length of time that the caramel spends and at a temperature and how high of a temperature it gets to. We have taken heat transfer and we have experience controlling temperature-dependent systems through the TC lab. So we wanted to apply this into making a PI controller for making caramels.
So here we have two different tests that we did to try and collect physical data in order to better tune our model. On the left, we have our doublet test. And as you can see, kind of no matter what temperature we put the stove to, it was going to approach or get to the steady state boiling temperature. This was a problem because this makes it difficult to create a model, but it's also a good thing because in a step test, like on the right, we get really good data and we can also create a really good model off of that. From this, we created a linear regression model where we found a Kp, Tau p, and theta p, and we had a sum squared error of 2,986 on our data, which is pretty good. And Parker is going to explain how we made a model out of this.
So we took our Kp, Tau p, and theta p, and we used aggressive IMC tuning correlations in order to find our Kc, Tau I, and theta I. We were then able to use these to create our PI controller. And since we did not have a temperature sensor that directly input the temperature to our controller, we had to manually input the temperature that we read off of the temperature sensor to our PI controller, which would then return to us an input for the heater, which we would then also manually adjust. So this left room for a little bit of user error as well as a little bit of time delay. But Brett will explain to you our controller's performance.
When we look at our data for our controller, we can see in the first 100 seconds that we had really a strong response from our heater and our controller, and it directly related to having a sharp increase in our temperature up to about 80 degrees Celsius. And our set point for the first phase in making the caramel was to get to about 113 degrees Celsius. And we were really happy with how it was going, and it looked like it was going to be done quickly. And then it quickly leveled off at about 80 degrees Celsius. And we were a little bit frustrated with that. And this comes from a misunderstanding that we had initially of going from heat transfer into mass transfer as the system started to boil and we were having a phase change. And so we then changed it to have a different Kc value to be a bit more aggressive. And we multiplied it by 2 at about 1450 seconds. And this brought up another temperature increase up to about 100 degrees Celsius, where it then leveled off again. And then at 1900 seconds, we multiplied our Kc by 4 to make it even more aggressive again. And that's when we were able to get up past 100 degrees Celsius and finally reach our set point. And so kind of what we learned from this was that it's a lot more than just raising the temperature. It's raising the temperature and then having a phase change as well. And so it's more than just heat transfer, it's that it's heat transfer and then mass transfer as well. And so in total, there's a lot that we were able to learn from it. But the key takeaway that we wanted to remember and would suggest to have more improvements on this study would be to include a physics-based model that would take into account this heat transfer and mass transfer together. I think an ideal controller would have parameters for when it's in the temperature, increasing the temperature results until we get to the phase change boundary, and having different tuning parameters to get through this phase change boundary until we can then reach our set point. And that's all we got. Thank you.